Discuss. Uh, Today we are going to discuss two of the aspects. One is we are moving on to descriptive statistics to inferential statistics. Then later we are going to have some hands-on experience with SPSS. So that's where we are planning to have this one. And in between we may not have any break, maybe a few minutes of break, and again we'll continue. Maybe we should be able to finish by 12:30 or 12:40 and or so. So we'll try to finish as I've got some other assignments. So let's continue with the inferential statistics. So remember how we are moved. First, we started with the descriptive statistics, where we thought the whatever the article, the statistics which we have calculated is merely to describe the data which you have at hand through various modalities. So it itself is what you call the modalities, like started with the graphical presentation, then we continued with the measures of central tendency, then measures of variability, then we saw how the normal probability curve would help us. Then later we got into transformed scores, and ultimately we ended up with the Sten scores. So today we'll go one step ahead, where the entire title is under inferential statistics, where this is very important when you talk about uh, the hypothesis testing, and when you want to generalize something, so your research is much fruitful. So a simple definition of inferential statistics is it is a field or branch of statistics where we are going to use advanced analytical tools for drawing conclusions about a population by examining the random sample. So you may not take a population for the study, but you are going to take a sample, what you call a representative sample. Then based on that representative sampling, you collect the data. Then you do inferential statistics, or you perform inferential statistics based on the hypothesis and objectives which you have formulated. Then later, you can generalize the findings to the population from findings from the sample to the population in general. Then remember, it has to be taken from the sample data, a sample mean, and later you draw a conclusion or inference. So that would be ultimate. So that's why once you say inferential, so it's a final conclusion drawn on the set of analysis you have made, and you try to say, okay, this is what it is. So that is why inferential statistics are more important. Let's slightly see the difference between inferential statistics and the descriptive statistics. For example, when you talk about descriptive statistics, it merely what you call, they are used to quantify the characteristics of the data through various modalities. Whereas in inferential statistics, we go one step ahead, and then we try to make conclusions or draw conclusions by selecting a population, selecting a sample. Then we derive that principle to the population. But you are using here advanced technical tools, which we'll be discussing in the very next few minutes. So for example, when you talk about descriptive statistics, uh, very important tools are measures of central tendencies followed by measures of variabilities. Both are required along with the other representations like which we have seen yesterday. Whereas here we go for in inferential statistics, the hypothesis testing and regression analysis are the analytical tools used. Though regression is comes under predictive statistics, still you can draw inference. That's the idea. Then coming back to descriptive statistics, as I said yesterday only, it tries to describe the characteristics of a known sample or a population which you have selected for your study. But here in inferential statistics, we try to draw inferences about an unknown population because you have taken a small what you call sample and then you proceed. So that's the idea where you go for what you call drawing inferences. And for example, some of the measures of descriptive statistics are like mean, median, mode, variance, and all yesterday we discussed. Whereas measures of inferential statistics are basically t-test, z-test, regressions, f-test. There are many one. So remember, whenever you talk about inferential statistics, try to understand that is for basically hypothesis testing from research point of view. Because with the descriptive statistics, you cannot go for a hypothesis testing because you don't generate a significance value. Whereas in inferential statistics, you are going to generate significant values and you are going to have test statistics for which you are going to check 95% confidence interval and 99% confidence interval. Based on that, you are going to infer or generalize your findings. So that's the idea under inferential statistics. Important not on inferential statistics are what you call, you should be knowing that they make use of analytical tools to draw statistical conclusions regarding the population data from a sample. So that's one important point where we are going to use highly sophisticated statistical techniques so that these techniques can be useful in drawing inference for a sample which can be extended to the population later. So hypothesis testing is one of the important part which we'll be discussing. Then whenever we use sampling techniques, they are used in inferential statistics to determine representative samples of the entire population. That is also more important, where sampling techniques are used for inferential statistics to get the representative samples of the entire population, because sometimes here we have to use a sample size. Remember, whenever you talk about a sample size, it is not what you usually refer as a 10% of the population. Not possible. So you have to go by specific criteria or specific formulae to calculate sample size. At least you have to follow Craig and Morgan's table. Please make a note where you can get for the each set of population what is the minimum required sample size. It's a Craig and Morgan table. At least if you type Morgan table for sample size, you get in the internet. So accordingly, you can calculate a sample size. So even that also useful in inferential statistics. So based on this, a brief note on inferential statistics, how important they are. Now, since all the time we are talking about inferential statistics are used in hypothesis testing, how exactly the flow chart would go. See now, this is a flow chart for steps in hypothesis testing. Now remember, you have to have a problem definition where what is your ideology or what is the aim of your study or title of the study. Remember, whenever you formulate objectives or hypotheses, see to that they'll fulfill the title as well as the objectives and hypotheses formulated. Because otherwise what happens, you collect the data and then later you find that okay, the data is not matching or data is not answering your objectives or hypotheses. So that's why yesterday also I told you, you consult a good research expert in your area or in your field so that they can guide you better. So having the problem definition, that what you want to do, now you clearly state the null and alternate hypothesis. That is also important. When you want to say null and alternate hypothesis, again which we discussed yesterday. So how to formulate hypothesis, where review of literature is a base for your what you call formulation of hypothesis. So now you have to clearly state the null and alternate hypothesis, and sometimes you may have to formulate the directional hypothesis too. So depending upon the condition, depending upon the nature of review of literature, now you can really start working on it, and you can state or formulate null or direction alternate hypothesis or directional hypothesis accordingly. How you are going to what you call plan it, that is more important. Then the next aspect is uh, once you have formulated the null hypothesis and any type of hypothesis, next you go for data collection. So you are already using standard tools for data collection, either primary or secondary data collection. Then once you collected the data, as I said, you compile the data, and while compiling the data, you have to filter the data, you have to discard the incomplete data. Remember, if a data sheet is missing more than 20% of data, your data sheet is missing by more than 20%, the ideal would be you discard the entire data sheet and go for a new data collection. That is usually advised. So once you have done with the data collection and filtered them, now it is a time for going for testing. So now you have to choose the relevant test statistics. So if it's a parametric data, you have to go for a parametric testing. If it's a non-parametric data, you are going for a non-parametric test. So depending upon the what you call type of data you have, accordingly you choose parametric or non-parametric test. Now once you choose on the parametric or non-parametric test, execute the test either by manually or using the software. That is more important. You can use the what you call software either manually or online or offline. Then execute the test, and now you see what is the determination of your significance level. Usually we say 95% confidence level, or the significance level should be at 0.05 level. So we'll be discussing what is this 0.5 and 0 in the subsequent uh, slides. So now we have chosen the critical value of 0.5, 0.05 or 0.01. Accordingly, we have to determine the degrees of freedom. That is also more important. So degrees of freedom usually n-1. In some cases, it is n-2. Depending upon the test statistics, you have to calculate the degrees of freedom. And this is required to find out what you call the critical value or the significant value, which is minimum required from a table. So remember, these critical values are available in textbooks at the end pages, where you can say list of tables. So most of the statistics books will have a series of tables and the appendix which can be utilized. Or if you are using a software, there could be a ready generation of the p values from the software by itself. So while doing that, you have to consider if it is one or two tail test. Now, when you talk about one tail or two tail test, in one tail test, we have got a definite outcome. So usually when we talk about one tail test, usually we have to look for a direction hypothesis. And if you have a direction hypothesis, it is better you go for a one tail test. But if you have got null hypothesis or alternate hypothesis, you usually go for two tail test, thinking that the scores have equal variances in the both the groups. Whereas in one tail test we may not have that kind of presumption, but in two tail test we have the idea of what you call equal variances assumed. Then once you decide, and now you get your test statistics, and critical value is there, your calculated value. Now you check with the table value or the test value which is there fixed. Now accordingly, if your value calculated is equal or more than the table value, then you say null hypothesis rejected. If your calculated value is less than the table value, then you say null hypothesis accepted. So whatever it may be. So if your test statistics falls in the critical region, then if it is falls under critical region, that is there's a value which is equal or more than the expected, then we say we reject the null hypothesis. And when it is not there, we do not reject the hypothesis. In fact, we accept the uh, null hypothesis. Whereas in the alternative or directional case, if the test statistics falls under critical region, we accept the alternative or directional hypothesis. And in the case of what you call uh, the test statistics, if it's not significant, we say alternate hypothesis or direction hypothesis rejected. So this is how the entire process goes in hypothesis testing part per se. Now we'll slowly move on to the types of statistics which we can be employed on a minimum level in social sciences. So we'll go to the next slide. So as I said, entire testing will go under four major categories. Your testing could be either parametric or non-parametric. And in the parametric, you can go for either for a difference or for a relationship. Even in non-parametric, you'll have either difference or relationship based test. So totally we have what you call four types of testings: parametric difference, parametric relationship, non-parametric difference, and non-parametric relationship. So these are the four sets of statistics which we'll be discussing immediately now. But before that, you have to do what you call consider few of the important things. For example, what kind of data you have? Is it a categorical data or numerical data? So once you say categorical data, automatically it will switch over to non-parametric side. And if it's a numerical data, you switch over to parametric side. So that is more important. So now the nature of data is very important to decide what kind of statistics to be applied. And remember, nature of data yesterday we discussed under 4 levels of measurement: nominal, ordinal, interval, and ratio scales. So now you should be able to decipher what kind of data you have. So based on that, now decide. Now the next thing is what is required. That is also most important. Are you going for a difference or are you going for a relationship? Because sometimes software gives what you call any kind of analysis if you highlight things, but you have to do, because software doesn't have a rational thinking. So you have to give the command, and once you give the command, it executes accordingly. So but you should use your mind, a common sense, where what is required, either you are going for a difference or going for a relationship. Please don't confuse difference for relationship and different relationship for difference. That's also not good, because you might end up with very spurious results. So that is also not expected. Then having all these two things, type of data and type of what you call kind of analysis you require, then now you have to decide which kind of test you have to apply, whether parametric or non-parametric. Now this is more important, because sometimes, as I said, you may have to go for a normality check. So once you are going for a normality check, sometimes though your data is parametric, you may have to forcibly do a non-parametric test. So again repeating, if your test data or your data which are collected, if it doesn't follow normality by rules, you should not do a parametric test. So you have to go for alternative non-parametric test. That is more important. So how to do that, we'll get into that later. Then later, you once you decide all, then while performing or executing statistics, are you going for a manual calculation with the smaller sample size? Yes, but with the larger sample size it will take more time, and your accuracy or precision in the calculations may be less. Even if you miss one score, automatically the value would change. So usually you prefer a software based calculation, or sometimes what happens is you may have to have ready what you call apps available in the net, where you can use them, uh, and you can still get the findings. Or sometimes people have got the habit of outsourcing it. So this is not my headache, okay, let somebody would do. So that's the idea, and I'll pay for it. But remember, there's nothing wrong in outsourcing, but you should be knowing that what is the idea behind outsourcing. You get the things fast, but what is been exactly been done you may not be knowing. So you should be having some theoretical background or knowledge about any test. So that's what our job is today, to start the theory first, and then slowly, if we get enough time, we try to check all the statistical tests. So this is being what you call things you have to consider before you start. So now we start the testing part one by one. So we start with the parametric difference based test. So once we talk about parametric difference based test, understand, usually we refer it as a t-test. Usually we refer it as t-test. But in t-test, if you think that there are two types, no, there are there are three types of t-test. So they're referred as independent samples t-test, paired samples t-test, and one sample t-test. And if we see the first type, that is independent samples test, that means what? Two groups drawn randomly from the population, and you try to establish a mean difference. That means what? You have selected a group of urban farmers and group of what you call backward area farmers. So you have got area as rural and very backward area. So you have got two areas, and you have selected few farmers regarding perception of theirs regarding what you call government policies towards farmers. Now your dependent variable is perception, whereas your independent variable is two levels. You have farmers from rural area and farmers from backward area. So now you can find out a mean difference in their opinion regarding government policies. So now it becomes independent samples t-test. Or on a very simple level, if you talk about attitude towards mobile usage, urban parents and rural parents. So parents from urban area versus parents from rural area. So you have two distinct groups drawn randomly from the population. Then you can apply an independent sample t-test. So idea is two groups drawn randomly. Now independent sample t-test comes with the rider. So what is that condition? So please note down, when your sample size is 30 or below, it is always wise to go for a independent sample t-test. And if your sample size is more than 30, it is better to go for a Z test rather than a T test. So please make a point. Independent samples T test usually comes or usually to be performed when your sample size is 30 or below. And if your sample size is more than 30, it's always wise to go for a Z test. Remember, independent samples T test goes by other names also. For example, earlier it used to be called as student t-test, which is still few of the textbooks have this naming called as student t-test. Then same name goes for two samples test. Sometimes you find the names as a two samples t-test, and there's another name for this test is unpaired samples t-test, because number of samples could be different in both the groups. They may be equal or they may be different. That is why it's called as unpaired t-test. So at single test goes what you call for different what you call what you call names. Independent samples is the latest nomenclature. Earlier it was called as student t-test. Then it was called as two samples t-test. It was called as unpaired samples t-test. So all the four names are same for only one test called as independent samples t-test. So that is regarding when two samples are drawn and you try to establish a mean difference and see that mean difference is significant or not. So that's usually we refer it as independent samples t-test. Whereas the second type of t-test is a paired samples t-test. So in paired samples t-test, the idea is the sample is paired for a variable. That means what? If you have got a pre-post design, if you have got before after design, so two measurements taken from a same individual either simultaneously or successively. So this is idea. When you take two measurements either from a same individual either simultaneously or successively. Now when we say successively, it is comes with the time gap. That's why I said pre versus post. That's why I said before to after. Or sometimes you can take the measurement simultaneous. Suppose you're taking your students data, marks in one subject out of 100, marks in another subject out of 100, still you can apply a paired samples t-test. Why? Because two measurements are taken from the same individual and having the similar unit of measurement, and the baseline must be constant. So in such cases we go for a paired samples t-test. The third type is one sample t-test. Now, when you talk about third type of test, that is one sample t-test, remember, though it is talking about a one sample t-test, actually it is comparing two means. So when you talk about two means, what is this mean? Now, in one sample t-test, what we do is, you have your sample mean. You collect data from your sample. Then what you do is you compare this what you call one sample t-test value with the established standard. That is more important. So you have a standard value which is already established from the previous researchers, and you don't require a control group here because the control values are already existing. For example, if you want to see, you are given a coaching program and you are seeing whether your students are achieving better. So you can keep a criteria of 60 as minimum out of 100. All the students were initially failing, and then you have given a rigorous coaching. So pre-test scores are like original scores of their achievement. Then you are given 3 months of intervention, that is you are given the rigorous training. Then again you are given the test and you have kept a criteria of minimum of 60. So in such cases, when you compare your group mean with an established standard mean, then it is called as one sample t-test. Then you might ask, where is the second group? Because we said two, what you call comparison of two groups. Yes, still there are two groups. Why? Because one is your group, another one is the mean which is derived from the another group which is from the large in nature. So most of the medical parameters are coming under one sample t-test. Because I don't know how many of you seen a medical report, especially for lipid profile. So if your doctor advises go for a repeat profile, so what you are going to do is they draw your 5 ml blood and give several repeat parameters. Could be total cholesterol, VLDL, HDL. There are several such what you call parameters are available. And in the bracket, first is outside the bracket, your what you call blood group value should be there. But inside the bracket, there are standard values are there. So your value should be within that high to what you call low range. And if it's going beyond, then the impression will be either hyperlipidemia or hypolipidemia, or it's a normal impression. Now remember, what we have done is we have compared the existing mean with an established standard. So that means what? You don't require a control group. So you can avoid a control group and invest more an experimental group, so that the data which you have obtained is more reliable and analysis is more fruitful. So that's the idea. Now, have you understood the three types of t-tests? So if you are not understood, please let me know. I don't mind explaining again and again. Types of t-tests, where you are going to have three types of t-tests. Anybody is having a confusion regarding t-test?
Sir.
Yeah.
Sir, I got little bit confused again with the first and the third one, sir.
Okay, in the first one, you have two groups drawn randomly from the population. Like you have got a group of boys versus a group of girls.
Okay.
Two groups drawn independently from the population.
Okay.
And you try to establish a mean difference.
Okay.
Whereas in one sample t-test, you have got only one group.
Okay.
And you try to what you call check the what you call the mean difference against
Standard one.
standard one. So that's why I gave a medical example where lipid profiles are all in the brackets are the standards, and your value will be compared against that standard. Then the impression will be formed. So are you clear now?
Yes, sir. Yes, sir.
Okay. Anyone else? So, but here your independent variable is split into only two levels. That's the idea. So because it's two groups, so independent variable is split into only two levels. One independent variable and one dependent variable you have. So go to the next. That is, suppose you have got more than two groups. So what you are going to do? So if you have got more than two groups, automatically you can use ANOVA. So when you talk about ANOVA, it is basically analysis of variance. So this analysis of variance is basically we refer it as F-test. The name F-test has come because the founder of ANOVA, called as Ronald F. Fisher, in his what you call respect, the notation F is given, and F-test is F is not frequency here. F-test stands for Fisher or Fisher's value. So when you talk about ANOVA, we try to establish a mean difference between more than two groups. So that means you should have minimum of 3 groups or more. But minimum of 3 groups are compulsory. Now when you talk about 3 groups, it could be you are taking a sample from urban area, you are taking a sample from rural area, and you are taking another sample from semi-urban area. 3 distinct groups. That means your independent variable is split into minimum of 3 levels. Now, ANOVA is number 20. Prakash Rathod sir, can you mute? Prakash Rathod sir, please mute.
Rathod sir, kindly mute your.
Number 20, Prakash Rathod, sir. Kindly mute your microphone. Okay, I think he has left the meeting with the microphone on. Anyway, we'll continue. So in one manner, as I said, you have what you call minimum of 3 groups, and you want to establish a mean difference. So automatically we refer ANOVA as an extension of t-test, because in ANOVA what we do is we compare more than 2 groups, whereas in t-test we compare only 2 groups. So that is why ANOVA is called as an extension of t-test, and the advantage is you can avoid multiple t-tests, and by doing ANOVA you can get the answer. So suppose you have got 3 groups A, B, C, and if you are going by t-test, you have to do 3 times t-test, A to B, A to C, and B to C. This can be avoided by performing a simple one-way ANOVA. So how to do it? We'll do it in the subsequent session. Then comes univariate ANOVA. So when we talk about univariate ANOVA, please try to understand that you have a single dependent variable, but you have one or more independent variables. So as I said, initially we started in one-way ANOVA, 3 regions: urban, rural, and semi-urban. The second independent variable could be gender. Under each one, you have male and female, male and female, male and female. So 3 major groups and 3 subgroups. Now you have got 2 independent variables. Now automatically it amounts to a univariate ANOVA, but still you have got a single dependent variable. That is more important. Whereas you have one or two, minimum of 2 independent variable. So anybody wants to know the clarification between independent and dependent variable? Or I think, are you familiar with these 2 variable ideologies, concepts? Anyone wants to know about in detail about what is an independent variable, what is a dependent variable? Anyone? I think you are quite familiar with them. So in univariate ANOVA, we use minimum of 2 independent variables versus 1 dependent variable. So that's why if you use 2 independent variables, it becomes 2-way ANOVA. If you are using more than 2 independent variables, suppose you use 3 independent variable, it becomes 3-way ANOVA. And if you are using 4 independent variables, it becomes 4-way ANOVA. So depending upon the number of independent variables, you are going to name it as 1-way ANOVA, 2-way ANOVA, 3-way ANOVA, or 4-way ANOVA, or so on. But anyway, this is how it will be done. Then you have got multivariate ANOVA, or sometimes it is referred as MANOVA. So the short form is MANOVA, where it is what you call here. Now the idea is you have several dependent variables versus several independent variables. Whereas in univariate ANOVA, we had a single dependent variable versus 2 or more independent variables. Whereas in multivariate ANOVA or MANOVA, we have several independent variables versus several dependent variables. That's why it's called as MANOVA. Now remember, whenever you talk about MANOVA, you have to invariably mention another index called as Wilks lambda. Please note this term. So if you are employing a MANOVA, you are supposed to provide a value called as Wilks lambda. Now this is important. Why? Because if you are publishing an article and you say you have employed MANOVA, it is going to ask, okay, what is the Wilks lambda value? So if you are employing MANOVA, see to that you are using Wilks lambda for the overall interpretation of the analysis. So what is this Wilks lambda under multivariate ANOVA or MANOVA? A Wilks lambda is an overall index which provides the information regarding the influence of all the selected independent variables over the selected dependent variables in a single what you call index. So that's why it's called as Wilks lambda. So again I repeat, it's nothing but influence of all the selected independent variables over the selected dependent variables in one index it gives. So if that is multivariate ANOVA, then another type of ANOVA is called as repeated measure ANOVA. So when you talk about repeated measure ANOVA, it's also called as RM ANOVA. And how many of you know about this? It's called as RM ANOVA. That means it's a repeated measure ANOVA. Suppose you have a design where you have got a pre-test, you have got a post-test, and you have got a follow-up. Means the same measurement goes 3 times. If the same measurement goes on the same individual 3 times, then we go for a statistics called as repeated measure ANOVA, or simply it is called as RM ANOVA. So here the idea is, as we have seen, if one way ANOVA is the extension of independent samples t-test, repeated measure ANOVA is the extension of paired samples t-test. So because in paired samples t-test, what we do is we just do pre and post, but here we add another index, another timeline called as follow-up. So we have got pre, post, and follow-up. So we have got the measurement 3 times continuous successively. Still we can go for a repeated measure ANOVA. Then the next ANOVA variant is ANCOVA. Now ANCOVA stands for analysis of covariance. So this is used when there are few of the variables which are confounding the results. Sometimes what happens, without your knowledge, your data may be confounded by other variables which are not planned in the beginning. So in the process of data collection or during the process of experimentation, some of the variables which are not at all considered for your analysis, they might intrude into the process of data collection, and thereby it can change the end results, but you have to control that. So to control that, we have to use what you call a test called as ANCOVA. The best example I would give for ANCOVA is the Corona batch students. If you have seen Corona batch students, when they got to degree level, when they came for admission to degree level, have you seen their scores? 95%, 96%, which is not possible when it comes on the regular examination process. And so much so that we had students even scoring 100 out of 100%, that is full marks, which is literally not possible, but they have got the what you call marks. Now if they get so much of marks in that way in PU, remember it is not because of their efforts. There is a confounding variable called as corona effect or corona batch. So that's why we, whenever the students are performing very bad, we use the terminology, are you from corona batch? This corona acted as confounded variable for increased performance, which in reality it is not so. So be careful about the what are the variables are really confounding. That is also important. So are you getting the clarity regarding for all these types of ANOVA? Or anybody wants to have more explanation? I don't mind giving explanation again. It could be one way, it could be univariate, it could be multivariate, it could be repeated measure ANOVA, or it could be ANCOVA. Anybody wants more explanation? I don't mind giving again.
Yes, sir.
So shall we proceed? Shall we proceed, or you want to have more clarification?
Yes, sir. One. Please,
Huh?
sir. Yes, sir, please.
Shall we proceed, or shall we have more discussion over this?
More discussion, sir.
Okay, madam, are you clear about the ANOVA part? What is ANOVA? So ANOVA test is done when there are more than two groups to be compared. Whereas if there are only two groups, we go for a t-test. You are clear about that, right?
Yes, sir.
So ANOVA is basically a method where it analyzes the variance between the groups, and it says whether the mean difference obtained between these three groups, a minimum, is significant or not. So that is starting by a one-way ANOVA, where you have got one independent variable versus one dependent variable, where the independent variable is split into minimum of 3 levels. So that's why I use the terminology urban, rural, and semi-urban. These are the three major groups, and you measure any variable under that, that becomes one-way ANOVA. Then the extension of one-way ANOVA is going to be univariate ANOVA, where the number of independent variables are being increased. So suppose you have got one variable, independent variable as area, like urban, rural, and semi-urban. I further split into subgroups: urban male, urban female, semi-urban male, semi-urban female, rural male, and rural female. So now we have taken second independent variable called as gender. So we have area as the first independent variable, gender as the second independent variable, thereby making two-way ANOVA. Why? Because your independent variable is split into two levels. Now I can go for three independent variables, where I started with the area, continued with the gender. I can now say developmental group. I can say children versus adolescents versus adults. So now this is the third independent variable. So I can keep on increasing the number of independent variables. So depending on that, I can use two-way ANOVA, three-way ANOVA, or four-way ANOVA. So whenever I say two-way, three-way, or four-way, the idea is whatever the number I pronounce, that many independent variables are involved in the analysis against a single dependent variable. Suppose you are thinking academic achievement as independent variable. Now academic achievement will act as, academic achievement act as dependent variable against the area, against the gender, and against the age group. So this is where we can go for univariate ANOVA. But in multivariate ANOVA, we make the things much more complicated, complex, where in MANOVA, we use several independent variables versus several dependent variables. In univariate ANOVA, what we did is we have taken area, we have taken the gender, we have taken even the age groups, three independent variables, but we have taken only one dependent variable, and that one dependent variable was academic performance. Now in MANOVA, there will be more such dependent variables. For example, could be their aptitude, it could be their intelligence, it could be their academic achievement, it could be their personality profiling. So you have more dependent variables versus more independent variables. That is why, since there are many independent and many dependent variables, then it's called as MANOVA or multivariate ANOVA. But remember, whenever you perform a multivariate ANOVA statistics, you have to invariably mention a test statistics called as Wilks lambda. Now, the next aspect is repeated measure ANOVA, where the same measurement is done 3 times minimum on a same individual or more. And this is the extension of paired samples t-test. So in paired samples t-test, what we did is we have taken a pre-value, we have taken a post value. But here we extend to a follow-up. Then it becomes a repeated measure ANOVA. So once we do a repeated measure ANOVA, we get a trend that the changes from pre to follow up, what could be the change in the scores and whether those scores are significant or not. So in such cases, we can use repeated measure ANOVA, and you can avoid several multiple paired samples t-test. Then you have ANCOVA or analysis of covariance, when you think that your data is being influenced by other unwanted variables which are not included in your data sheet. So suppose you want to measure academic performance of PUC students. Now there could be a lot of variation on a particular year when corona batch was announced, when the PUC students were given free scores. They have not undergone any tests, but they are just given the scores. So much so that 100 out of 100, which is not so possible in general. Whereas the other batches have scored 70%, 70% and all, but this batch 100% pass. So now, why that increased marks? There is a confounding variable called as, or intervening variable called as a corona effect. So then we have to balance that corona effect. In such cases, we cannot use directly a simple ANOVA, any variant of ANOVA. We have to go for analysis of covariance because you have to balance the effect of covariant like corona. Are you getting it?
Thank you.
Okay. So that's the one thing. Then we go for further. Whenever you use ANOVA, we refer it as it's a macro level analysis. So you have to further find out the micro level of analysis where, suppose if you have got three groups A, B, C, and your F test says that there is a significant difference. Now you have to go for the multiple comparisons, whether A to B is significant, A to C is significant, or B to C. So possible mean comparisons in pairs and whether those pair differences are significant or not are done by any one of the following tests. So it could be LSD, least significant difference, or it could be DMRT, that is Duncan's multiple range test, or it could be Sheffy's test or Sheffy's honestly significant difference test, or Tukey's post hoc test, or Bonferroni test, or Dunnett's test. These are all the tests which are used in multiple comparisons whenever your F value is significant. So that's the idea where you use the post hoc test, but it will be used only when your F value is significant. Chanapa sir, kindly mute your microphone. Chanapa sir, number 37. Kindly mute. Chanapa sir, please mute your microphone. Your microphone is on. Okay. So that's where we finish the first set of analysis called as parametric difference. Now we go for parametric relationship based tests. Now when you talk about relationship based tests, remember we are going to talk about a correlation and a regression. So in the parametric relationship based test, yesterday we discussed the minimum and maximum correlation coefficient, how they can vary and all, -1 to +1. And in the parametric form, the correlation analysis used is Pearson's product moment method. And sometimes we have to use partial correlation. Why we have to use partial correlation? So partial correlation is used when you find that the existing relationship between two variables are being influenced by some other variables which are not in the study frame. So in such cases, you may have to use a partial correlation. A partial correlation is usually required to control or balance the effect of other variables which are not necessarily included in the data collection process or in the research protocol, but you get to know that they have influence over the end product or the outcome. In such cases, you tend to apply a test called as partial correlation rather than simple correlation. And we go ahead with the other aspect, like in the case of regression, where, as I said earlier, correlation gives the idea of the relationship between two variables, whereas regression gives the idea of prediction. Suppose you want to predict something, so this will come through, the prediction comes through a simple method called as regression. So if correlation gives the idea of mutual relationship between two variables, the regression says what is the rate of change. So once I refer to the rate of change, remember the rate of change here refers to as the x increases, what happens to y. So as the x increases, y might decrease, then the rate of change is negative or minus. If as the x increases, y also increases, then the rate of change is positive. So depending upon the nature of two variables, we can decide regression analysis. And there are two types, simple versus multiple regression. So in simple regression, we have got one x and one y, where y is called as major predictor or major dependent. X is the independent variable, and if x changes by 1 unit, what is the corresponding change in the y unit? So that is the idea where we talk with the simple regression. You have one independent variable and versus one dependent variable. Whereas in multiple regression, you have several independent variables versus a single major dependent variable. So the best example for a simple regression is, if height increases by 1 centimeter, what is the corresponding rate of change for the weight? So suppose you are correlating height and weight and you are getting a positive correlation. Now the next job is rate of change. If height is increased by 1 centimeter, what is the change in the weight corresponding change? So you take data from several samples and apply a simple regression, then you get a rate of change. So but you have here height as independent variable, weight as dependent variable. That's where you have got one independent and one dependent variable, and simply referred as a simple regression. Whereas in multiple regression, you have got several independent variables and only one dependent variable. For example, again coming back to student achievement, a student achievement can be decided by several independent factors, starting with the genetics part or hereditary part. Then the next is number of study hours, then motivation to study, teacher effectiveness in the class, classroom environment. You can have several dependent variables and regress on one of the variable called as academic achievement. Then you might get a major predictor. Whatever the dependent variables we have entered into the equation may not be predicting the academic achievement all. So only few of the dependent variables might predict the academic achievement of the student. So in such cases, we have to use a regression method called as multiple regression, how several independent variables predict a major or a single dependent variable. So I have given two of the examples. You can check more. So this is where parametric relationship based test, where you have second line we have finished. We finished with the parametric difference and parametric difference. Now we go for non-parametric difference based test. Now it's a third set of analysis. So when you talk about the third set of analysis, basically we start with the chi-square test. Now when you talk about chi-square test, it is basically to find out the frequency difference between two or more groups. So that is why it's called as chi-square test. Now when you talk about chi-square test, there are two types of chi-square tests. So the first type is chi-square test simple, and second one is chi-square test of independence. So if you are using directly a frequency difference, for example, suppose you are using a questionnaire and you have got responses on strongly agree, strong agree, cannot say, disagree, and strongly disagree. You have got varieties of responses. You can apply a chi-square test for such data, and you can find out whether your data, whether there is a response are more on agreement side or more on disagreement side, or it's more on neutrality. Now this can be done through a chi-square test. And the chi-square test of independence comes when you divide into cross tabulation. Suppose same what you call chi-square, if you bifurcate for male and female responses, So on one side, you have got gender as male and female. Otherwise, the cross tabulation would be the responses: strongly agree, agree, cannot say, disagree, strongly disagree. Then you can further find out through chi-square test whether males are what you call agreeing more or whether females are disagreeing more. So what is the pattern of responses for male and female? You can check, and whether this pattern is significant or not, that can be checked through a test called as chi-square test. Then as usual, you have got Mann-Whitney U test. So Mann-Whitney U test is a counter test. Try to understand, it's a counter test for independent samples t-test. Later I'm going to provide you a table where it gives the possible tests and the type of data required under parametric or non-parametric conditions. So in Mann-Whitney U test, you compare two groups randomly drawn from the population like independent samples t-test, but the data here is qualitative data or non-normal data you have to apply in Mann-Whitney U test. Wilcoxon signed rank test is an alternative for paired samples t-test. So that's the idea where you are going to use a paired samples t-test there. Whereas in non-parametric side, you are going to use Wilcoxon signed rank test. There you used a simple one-way ANOVA. Here you are going to use Kruskal values one-way ANOVA. But remember, in non-parametric data, you don't use your data original. You convert them either into ranks or into signs. So only SIGNS plus or minus, or you convert them into ranks. So the data reducibility is very high because you are not using the original data per se. You are using the converted data either into ranks or into symbols or signs. So that is why the article, when you talk about non-parametric tests, people may not like the idea that all the time you're using non-parametric tests, but sometimes you have no choice. Suppose if the data ends up in only frequencies, I think then you have to go for a non-parametric test, but try to do as much as parametric tests. That's usually people recommend. So these are the non-parametric difference based tests. Likewise, we have got non-parametric relationship based tests. Now in non-parametric relationship based tests, one of the technique is called as Spearman's rank difference correlation. Now in parametric we had Pearson's product moment correlation, whereas here we are going to use Spearman's rank difference correlation, and sometimes we have to associate them contingency coefficient. Suppose you have got a what you call data set in a cross tabulation like 2 by 2, like 2 rows by 2 columns, or 3 by 3, 3 rows by 3 columns, 4 by 4, 4 rows by 4 columns. So when your data is in the cross tabulation of 2 by 2 or 3 by 3 or 4 by 4, where number of columns are equal to number of rows, then invariably you have to use a contingency coefficient test. Now when you talk about the contingency coefficient test, remember it is basically how much the row data is dependent on column data and vice versa, how much column data is dependent on row data. So this is where you are going to use contingency coefficient test. When the unequal number of rows and columns, you can easily go for a Kramer's V test. So that also can be done. And there are higher forms of regressions which are mixture of both parametric and non-parametric data. They are called as logistic regressions. So I don't know whether in social science you do it, but anyway, for your reference, you can keep this in your mind. So in logistic regression, we usually have the data as non-parametric as our major dependent variable. Your independent variables could be parametric or non-parametric. You try to regress on the major dependent variable, then you can derive what are the factors responsible for the dependent variables, what you call occurrence. So for example, if you're talking about infant mortality, suppose you are taken the data from 500 live children live infants born and 500 infants dead. If you take their what you call data altogether and collect all the other information, now remember survival versus dead is the dependent variable, but there could be several other what you call variables are included to influence this. They are called as dependent variable, starting from the mother's age itself. Mother's age is young or old, that can contribute to infant mortality. Then household condition, nutrition supplement, mother's bad habits like smoking or drinking. Then if you go for medical grounds, there is a Apgar scores at 1 minute and 5th minute. Birth order of the child, attitude of the significant ones, whether wanted child or unwanted child. So you have got several such variables. Then you regress on the death or survival of the child data. You might get the major predictors that what really what you call contributing to child mortality or infant mortality. Accordingly, you can advise the government or the agencies to use, okay, these are the factors which are predicting the infant mortality. So that is why you have to follow these strategies. Now today, I don't know how many of you know, in rural areas, the midwives or nurses from the primary health centers, they go to each household and they search for the pregnant females and they forcibly make them to eat vitamin tablets. And whether you know these habits are there or which this kind of routines are there in the rural areas where these midwives or senior nurses, they do a household survey, look for the pregnant women, then they they keep a diary and they forcibly tell them to take vitamin tablets. Why? Because one of the major reason for infant mortality is the nutrition deficient food or vitamin deficiency. And if the pregnant mother takes the vitamin rich food, I think definitely the infant mortality can be avoided. This research is already done earlier and they had suggested that, okay, this is the reason for what you call infant mortality. So supplement with these pregnant females with the vitamins, definitely infant mortality is reduced or will be reduced. No, that is a benefit of binomial regression or multinomial regressions. See how you can see how statistics is useful for even for policy making. So that's what it could be, a bicycle scheme, it could be even a midday meal scheme where statistics has helped them. Okay, this is where you can improve the conditions of the public and the society. So these are relationship based under non-parametric tests. Then again, I'm repeating, what are the important considerations while doing a statistical analysis? First of all, you have to check for its normality. This normality check can be done, as I yesterday said, can be done by a Shapiro-Wilk test when n is less than 50, or it can be done through Kolmogorov-Smirnov test when n is more than 50. Then if the data is not following normality, apply non-parametric test even if data is parametric. This is very important because the standard journals would definitely ask, have you what you call subjected your what you call data into normality check? And if you said no, they might reject your paper. So apply the normality check test, and if the data doesn't follow, use non-parametric test instead of parametric test. There are enough alternatives are available. Then if the sample size is small, then it's wise to use a non-parametric test, not a parametric test, though your data is parametric. Why? Because the data which you apply a statistics for a smaller sample is what you call may not be representative of the population. So automatically it will become a distribution free population. So for a distribution free population, we don't use parametric tests, we use a non-parametric test. So if the data is less, don't apply parametric test, go for non-parametric test. Suppose your data is only 5 or below, please don't apply any statistics. It amounts to abuse of statistics, inferential statistics. You can just go for a descriptive statistics. So again, I'm repeating, if data is very less, it is not wise to use any inferential statistics. Of course, the software gives you the analysis, but the authenticity of the applicability of those findings are still under question. So please keep these things in your mind, and we'll move on further. The significance levels. This is where majority of the people have got doubt. What is this significance? So usually we talk significance at 0.05 level, 0.01 level, and 0.001 level. Accordingly, we refer it as 95% level of significance, 99% confidence level or significance, or 99.9% significance level. Now remember, in statistics, the significance criteria or pass for significance is very high. Whereas our student pass is only 35 out of 100. I don't know how many of you know about this. 35 is a minimum marks pass. Whereas in statistics, that minimum pass for significance is 95. So a very, what you call, very rigorous condition here, where your data will be into what you call the level of 95% significance. Now, what is this 95% significance? Suppose you repeat the data collection 100 times, or suppose you repeat the experiment 100 times, you should bound to get 95 times the same result. That is what you call the significance. Then only we say pass in significance. Even if it is 94 out of 100, we say it is non-significant. Your significance level would be 0.06 here. Your significance level is 0.06 here. So automatically the confidence is 94%. We say it is non-significant. So the minimum significance level is 95%. Please understand this. Minimum significance level is 95%. And on the higher level, we go for 99% level of significance or 0.01 level. Then it's called as highly significant. We started with the significance, then we go for highly significant. Now the significance level increases. Now, if you repeat the data collection 100 times, 99 times you are bound to get the same result. Only one time you can miss. We make it more severe. That is very highly significant. If you repeat the experiment 1000 times, 999 times you are bound to get the same result. So that is referred as very highly significant. So depending upon the significance level you have obtained, you can interpret the data accordingly at 0.5, at 0.1 and 0.001. And if it is 0.06, that is 94, then you immediately say it is non-significant. So the significance level which you obtain, more towards 0 is significant, more towards 1 is non-significant. So please keep in that mind while interpreting. So 0.05 is your cutoff. That is 95% level of significance. Please keep in your mind. Then once you know the significance, now comes how to verify the hypothesis. So as I said, you may have formulated the null hypothesis or you may have formulated the alternative or direction hypothesis. In the beginning only I said null hypotheses are meant for rejection and alternate hypotheses are meant for acceptance. Sometimes what happens, you have formulated the null hypothesis and your results are significant, you reject the null hypothesis. But sometimes what happens, you formulate the null hypothesis, but your results are non-significant. You have to accept the null hypothesis, which is not expected, because what we said is null hypotheses are meant for rejection rather than acceptance. Whereas in alternate or direction hypothesis, the hypothesis have to be accepted, because whatever you have said, it should be proven. And whatever you have said, you cannot say. If it is not proven, then you reject the null hypothesis. Now you see the first two formats, null rejection and alternate what you call direction hypothesis acceptance. This two highlighted one is now the approved format or expected one. But sometimes what happens is, you will have what you call the problems. What is that? Sometimes you are forced to accept the null hypothesis and forced to reject the null hypothesis. See now this part. Now this part which is highlighted one, null accept and alternative directional reject. will give the idea of type 1 and type 2 errors. So yesterday I mentioned what is that type 1 and type 2 errors, which should not be done much in research, because the more type 1 and type 2 errors are being done, then it's not a good research. So in null
Sir, can I interrupt, sir?
huh?
Can I interrupt for a second, sir?
Yeah.
Sir, if we are forced to accept the null hypothesis, for example, if I am doing a test on comparing the students' attendance with the performance,
Okay.
and in the corona case, I may get a result wherein the attendance has no impact upon the performance.
Madam,
Students might have
you are
studied on their own.
not conducted the test. You have awarded the marks.
Okay.
Huh?
Okay.
Huh?
No, online, sir.
You understood?
Yeah.
You are not considered any punctuality or any C1, C2. They are not given anything.
Yeah.
And that's why I said it's a confounding variable.
Okay.
Corona condition itself was a confounding variable for students, which for many of them it worked as a boon. For few of them it worked as a bane. Okay. So now, if you are forced to accept the null hypothesis and if you are forced to reject the alternative direction hypothesis, you end up with the two types of technical errors called as type 1 and type 2 errors. So what are those type 1 and type 2 errors? So before we getting into type 1 or type 2 errors, I given a extended chart where you can use this chart for data nature as well as you can use for this the data nature as well as for what you call application of statistics, which I'm not going to talk much about it. So you have got different kinds of levels of data. You have got parametric side applications and non-parametric side application. One table will give you the complete picture that what you can do the best. Anyway, this has already been discussed, so you can what you call keep this as a ready reckoner. So that's a comprehensive table. So now we'll move on to type 1 and type 2 error. So type 1 error, what you call when the tested hypothesis is falsely rejected. Now the idea is, it is when you say found something, but that something is really an error. So this is called as bogus alarm effect. So I'll try to give an example. What is this bogus alarm effect? Now a type 1 error is like analogy is like, suppose you are on a what you call 10th floor in a big story building, and suddenly the fire alarm comes. So what is your next job? Fire alarm comes from all the sides. So what is your next job? You try to vacate the place. You want to evacuate others so that you want to get escape from the fire. But later you come to know that there was no fire. The alarm was by mistake. Now this is called as bogus alarm effect. Something is, when you say you found something, but that something is really an error, so which has not happened. So in research also, sometimes what we do, something which we don't do, but still we project that we have done it. That is type 1 error. But when it comes to type 2 error, it is when you don't find something that is there. So there was a fire in the 10th floor, but there was no alarm. Now are you getting the severity of type 1 and type 2 errors, where you can say it is there, but it is not reported. Now on a simple level, where a person goes for HIV test, in fact he doesn't have HIV plus, but the test says he's HIV positive. Now remember, the person doesn't have HIV positive, but the test claims that he is HIV positive. Now that is a type 1 error. The example for type 1 error. Go to the second condition. The person has HIV plus, but the test says no. Much more dangerous. Now you understand the type 1 and type 2 error issues. So this type 1 and type 2 errors may have their own implications while what you call interpretation, and more of type 1 and type 2 errors will indicate that you are not followed a sound research methodology. And there is a type 3 error. This is from the what you call researcher side. A lazy researcher who doesn't want to collect the data, he just sits and collects the data by other means. Incompetent or willful ignorance of the truth. Some researchers will do this, where what they do is they they remove the data which they know if they add the data, you will not get the desired results. So they remove completely that data. Sometimes they manipulate the data. So all this amounts to willful ignorance of the truth, and that will amounts to type 3 error. So usually we have type 1 error, type 2 error, as well as type 3 error. Type 1 and type 2 error from the hypothesis side, whereas type 3 error is from the researcher side. So please try to avoid all of them for a very good research. So with this, I'm finishing the theoretical sessions on inferential statistics. So any doubts before we move to the next what you call slide, or next to connecting talk is use of SPSS. I know it is little technical in nature, but if you have got any doubt, you can ask me. Any doubts? Okay, if there are no doubts, we'll have a quick break for 10 minutes. Okay, because I know you also will be continuously bombarded by the talks. So we'll have a quick break of 10 minutes. So sharp 11:35 will rejoin, and another and we start working with the SPSS. Is it okay? We'll have a short
Okay,
break
sir.
of we'll have a short
Okay,
break
okay.
of only
Okay, sir.
Okay, sir.
10 minutes. So we'll rejoin at 11:35.
Okay, sir. Okay, sir. Thank you.